actually we were talking that the electronic spectrum, electronic excitation spectrum. What
Yes.
does this mean? This means that whenever we have a system, then if it is a system of electrons, then when one of the electron jumps from low energy state to high energy state, then we say that
This
system is
yes.
an excited state. And the problem with DFT is that when we calculate the Kohn-Sham energies, those Kohn-Sham energies are not the same as the energy uh, of the system in energies of the states of the system between which the system uh, make excitation. That is when a particle leaves uh, low energy state and go high energy state. So this uh, these two states are the states are called excited states of the system. But the density functional theory does not predict correctly those sort of excited state. So we need some sophisticated theory. Also, the second point here is that a photo emission experiment then measure the excitation spectrum of solid with the presence of hole. Uh, when actually the I have to uh, give you some feeling for the quasi-particle energies and meaning of the quasi-particle. Let me uh, let me see if I can have some sort of explanation, some sort of. These are actually excitons. These are the excitons which once upon a time you were asking me what are excitons, and I at that time
Yes.
told you that I don't know the exact meaning what is meant by excitons. But now I
Okay.
understand what are the excitons. So I am actually try to give some feeling to you that what are excitons. An exciton may be defined as the bound electron-hole pair. An exciton is may be defined as a bound electron-hole pair created by some excitation process. Create some excitation process. It is the same excitation process as already I told you when one of the electron from some energy level go up to the next energy level, and when this electron leaves the one energy level and it leave behind the hole. So the idea is that uh, this this electron and hole are not independent of each other. Actually, they behave collectively. They behave actually collectively. So this
Okay.
is something different as compared
Okay.
to the simple theory in which we say that there is an electron in low energy level and it
Yes, the
goes to the
jump.
next energy level. This is entirely something different. We will say that this electron is not independent of the vacancy which it left behind when it go from low energy state to a high energy state. So here
Okay.
is a picture which depicts this sort of understanding. For example, here an electron go from valence band to conduction band, and this is
Yes.
the hole, and this is the electron. And the basic theme is that in case space, this electron and hole behave collectively, and this is called Mott-Wannier model of an excitation is the bound electron. An excitation is a bound electron pair moving through the crystal. Whenever there is some electron and it go to excited state, then the dynamics of that electron is not the dynamics of that single electron. It is actually the dynamics of a pair, that is electron-hole pair. This is what is called Mott-Wannier model. And these the excitation of this system is actually related not to a single electron, not to a single hole, but it is the collective behavior, collective dynamics of this electron-hole pair throughout the crystal. So the creation of this electron-hole pair in a crystal is termed as the excitation of this system, and this excitation of system is called actually the exciton.
Excitons.
This sort of understanding is related to the excitons.
Yes.
So
I think that's what we are going to study in my work.
Yes, actually,
yes, that is the missing information.
We want to solve such equations in which we want to find directly the energy of this electron-hole pair collectively. This electron-hole pair can be described as a single particle, which is actually called the quasi-particle.
Yes.
What does this mean? This means that in crystal, this electron-hole pair can be described. The collective behavior of this electron-hole pair can be described as a single particle, which we call the
quasi-particle.
Quasi-particle, and the the description of this particle is done through the quantization, and as a result of quantization, the particle which we name like photon is an exciton.
Okay.
So this is actually the true meaning of an exciton. Exciton, if I can, if I am able to give you some feeling of that, what is meant.
Yes. Yes, actually, of
an exciton, or other words, some excited states of the system. So in order to find the energies of the exciton, this is called the Wannier equation. And this is one body Schrödinger equation type, this Wannier equation. And in this Wannier equation, here we depart from our usual convention of employing atomic units and explicitly indicating the fundamental constant. Actually, this is talking. It is talking about the use of different units. This equation just look like Schrödinger equation for hydrogen atom, except that the free electron charge is reduced by the dielectric constant ER. Because here we use the dielectric constant, because E over R is the charge of electron here. So it is reduced, and the free electron mass is replaced, and this free electron mass is replaced by the reduced effective electron hole mass. And how electron hole mass is defined? It is defined as 1 over E. Electron hole mass is equal to 1 over electron mass plus 1 over hole mass. So this is the actually problem we want to handle, and then we want to describe electronic spectrum or optical spectrum in the presence of excitons. This is the basic theme which would be our problem in theory side. That is, we want to find the optical spectrum of our material in considering the excitons, and due to the presence of these excitons, there would be two type of modification in our spectrum, and we expect from the theory that these two type of modification should be depicted with the by the theoretical theoretical calculation according to our theory, and because these two modification are actually observed in case of true spectrum. Bound excitons appear as discrete lines below the band edge. Bound excitations appear as discrete lines below the band edge EG, and form a Rydberg series with energies. And the energies are E, and different energies are these energies of these excitons will what does this mean? The author is actually want to tell us that the spectrum of spectrum related to these excitons will have the energies below the band edge, and also the form of the energy is equal to En, is equal to minus E naught exciton divided by N square, made relative to Eg. Here Eg is the lowest exciton binding energy given by this formula, and the exciton bound radius is given by this.
Is this a dot or what? I saw it's something of dot square.
Yes.
Okay. So it's just a dot.
Yes, it is dot mean something special to the excitons.
Okay.
Above the band edge, second modification, above the band edge, the absorption is strongly enhanced. Absorption is strongly enhanced due to the excitonic continuum states. Due to the excitonic continuum states. This sort of, and these are the lines we are talking about. Schematic optical absorption spectrum of direct band gap insulator in the region of the band edge. Dashed line, independent particle picture. In case of independent particle picture, the energy absorption spectrum should be like this. But when we see the full line of modification spectrum due to excitation, excitonic, it is like this. This is the line, this is the line, this is the line, this is also a line, and then there is a continuum.
Okay. So what
This
does the continuity means?
means above this zero level, the energy levels of excitons are also not discrete, they are continuous.
Okay.
Below this edge, band gap edge, the
They
excitons
are
are
discrete.
discrete. So
Okay, I've understand.
this is from this picture.
Okay.
So Curie must give us something, the feeling of this. Next, next is something to consider, which would be helpful for us to understand it, as well as it would be helpful for you to understand what is going on.
Okay.
Here is the figure 12.27 shows the experimental data for excitonic, exciton,
Right.
excitonic Rydberg series in uh, Cu2O and GAAS, confirming the general feature of excitonic spectrum discussed above. Because we actually expect the excitation spectrum like this.
Sun kawo ruwa.
So we decided, should we are we observing something like this? So in that case, figure 12.7 is shown here. What is
Okay.
about figure left? One photon top and two photon bottom. Absorption spectrum of Cu2O. This is taken from right. High resolution absorption spectrum of gallium arsenide. These are something shown as a spectrum, because here is the 1s peak, here is 2s peak, and here are two other peaks. I am not very sure about how we should explain these peaks. And also, this is just spectrum. Mean here is a peak, here is also a peak, here is also a peak, and then it goes to infinity, just like uh, hydrogen spectrum. Here,
Yes.
one peak is here, second peak is here, third peak is here, and then after that peak, there here goes to continuum, and after that, this is predicted by one particle theory, but this is actual experimental observation.
Okay.
So actually, we have to talk, we have to understand, or we have to make some observation like that for our system.
Result. Yes.
So
No,
one
I
thing,
think
another
if there should be,
here is another,
if there should, yes,
yeah,
think if there should, can we interpret our result based on this format?
yes.
Then
So
I
here
think,
is another
inshallah,
observation of imaginary uh, part of dielectric function for the system. Here is experimental observation in the circles, black
okay,
dots,
yes, big cycle, yes,
then the result of random phase approximation, and as well as
yes,
the time dependent
time dependent
LD.
LDA.
So in both our case, we say that there are two peaks, E1 and E2, in experimental observation. But in case of RPA, random phase approximation, and the LDA, here is a peak. Peak is also not on the proper place as well, and there is no second peak. Yeah, but just there is a some a low energy color here is some
Yes.
color, but it is not like two peaks, E1 and E2. So explanation of these things is written here. And also another observation is that with the help of the corrections by handmade corrections, the spectrum may be made more close to the experimental observation. For example, failure of local approximation. Here is discuss the failure of local approximation in this paragraph. It says that the imaginary part of dielectric function of silicon in region where direct interband transition set in. Where direct interband transition is set in. The experimental data X beta characteristic double peak structure above 3 electron volt. The peak labeled E1 located right above at a band edge has excitonic character. This means that as we say that this peak, this E1 peak is of excitonic character. Are you listening?
Yes.
Okay. This is of excitonic character because this is just below the edge of the gap for silicon.
Okay.
Then what is the problem? When the experimental data are compared with the theoretical result obtained using RPA and ALDA, two main problems are observed, namely that the onset of absorption is redshifted by about half an electron volt. And the first excitonic peak is almost completely absent, except for weak shoulder. Actual peak should be here, but it is shifted toward this. Okay.
Yes.
And
Yes.
also in this spectrum, there is no second peak, except here is a shoulder. It is not a peak.
Shoulder. Okay.
So this is the problem with theoretically calculated excitation spectrum based on random phase approximation as well as ALDA.
LD.
So what he says, this observation is by no means in an isolated case, but rather is a very characteristic of the performance of DFT for optical absorption spectrum for insulator, standard local and semi-local exchange college functional universally fail to describe the excitons. So this is the problem with the DFT.
Okay.
Because in DFT, we use local or semi-local exchange correlation functional, and they universally fails to describe the excitons. This means that even simpler system, even in complex system, even in there is no one system in which these local and semi-local functional describe some exciton. They, according to the result of this semi-local and local exchange correlation functional, there would be no excitons at all. And the second problem is the underestimate the optical gap, and also it underestimate the optical gap. On the other hand, the spectral feature of many semiconductor and insulator can in fact be quite well reproduced if the wrong optical gap is corrected by hand. This is also the important point to understand because sometimes we use the same standard local and semi-local exchange correlation functional, but the underestimation of these exchange correlation, underestimation of the band gap in these exchange correlation functional, we correct them by hand. What does this mean? This means that we actually by hand uh, use the difference, uh,
Okay.
which was not which was underestimated by the by these exchange correlation functional. During calculation of during calculation of this during the calculation of optical spectrum, we actually not use the band gap as calculated from DFT, but we use the band gap which is corrected by hand. For example, if the band gap of silicon is found to be 1.6 electron volt by DFT, and we know that it is actually 2.6 electron volt. So we will use not the value of 1.6 electron volt, but instead we will use the value of 2.6
6 electron
electron volt
volts.
by adding 1 electron volt by ourselves. So this means a rigid shift of the due to this we use a rigid shift of dielectric. Due to this use of corrected band correction by hand, the rigid shift of dielectric function is made. This is described in this paper in 2000 uh,
Costra. 2000,
in 2000 by
2000.
uh, Cotes,
It's Costra.
Kotstra.
Costra.
Uh, then then what has happened? It happened that it actually shifted the peak. What does this mean? This means that due to this sheep will be actually shifted to the correct value here.
Yes.
But uh, this shift would not produce at all this first peak, which is due to the excitonic character, which is of the excitonic character. So this is due to this reason, we need some theory which should describe the excitonic properties of uh, electronic system. Another here is an as an example, the dielectric constant of ZnSe is shown in 2.12.9. This is the figure where dielectric constant for material ZnSe is calculated. And here is the comparison of experiment and theory. You can observe that dotted line is the theoretical experimental result, and solid line is the theoretical result. And due to this this theory is an example in which we have shifted the band gap by hand, or corrected the band gap by hand, and
Yes.
plotted these uh, uh, plot these dielectric constant for this material, and it shows almost the
The same
behavior
thing.
is almost in agreement with the theory, because one peak is expected here, and theory is also showing that this peak is here. One peak is expected here, but theory is also giving the peak, but it is peak. This peak is very high as compared to the experimental result. But actually, we see that there is a peak and then dip and then a peak. Again, there is also a peak which is experimentally observed, and as well as the theory is also predicting that there should be a peak. And again, there is the theoretically justified behavior. So again, here is also theory is almost giving the same behavior as experimentally observed, because here is the peak, here is a peak, here is also a peak, and theory also give here a peak, and and experimental results are also showing there some ink here. So, uh, but uh, in, the result is that, the conclusion is that even after making some uh, uh, by hand correction to the band gap of material, and then using that band gap to calculate the optical properties of the material, may experimental and theoretical results may seems to be coincident, but again the problem persists that excitonics spectrum effect could not be explained by the theory. Even we have made the correction with the band gap. So what does this mean? This means that there is something other than the problem of the band gap, which is which cannot be included through in the DFT based approximation. So this
Okay.
is another evidence that we actually have to include the many body effects, because this
Okay.
excitonic effect is a purely many body effect. So we
Okay.
need some modifications in our calculation. And GW approximation in one way or other is actually going to include those effects, those excitonic effects, and particularly GW approximation is particularly going to include the many body effects, and in particular, in case of optical spectrum, it is the uh, Bathy-Splitter equation, which gives these excitonic peaks, and there would be a complete story behind these behind this many body corrections to the theory. And if someone want to understand how this is going on, he should build the complete story using many body theory through the response function, and as well as the use of many body perturbation theory as used by the Yongo code.
Okay. So it's now I start to understand really what is going on. Actually, of so are you listening?
Yes, this time.
Please, I will send you my proposal.
Oh,
There is actually a place where he are you listening?
yes.
There is actually a place where he drew some tables on how to use the Yambo code for the calculation. So I don't know whether you might understand something that I not understand,
Uh,
because I really want to form the slide for the methodology actually. So
Actually, you should first try to meet your supervisor tomorrow, and if he will guide you what should be the points there, then I may help you to refine those points, or I may help you to understand those points, because mm, uh, I don't think what uh, what is what your supervisor is thinking, because he would be somewhat familiar with the methodology if he has
yes,
done some work. That then it would be easy
yes,
for him to guide you.
Okay. Let me see if I can see him.
Yes.
I pray I see him because it's like the something happened between them and the government. That the government did not pay them their money on due time.
Okay.
So we are just waiting for the outcome, whether they might shut down the universities or not. We don't really know. Because I heard that the whole of the professors in my country, they're in the state capital meeting,
Okay.
actually.
Why state
So
is not owning your universities?
no, actually, there are some money for research allowance and all these publication and all those things that the government is supposed to pay them. So I think the government had been promising them time by time, it's failing them. So and now it's some month election in my country. So I think they're going to use that as a avenue to pressure the government because the current government cannot afford to go